All right, so section 26 is on concavity and the second derivative. Okay, so concavity is kind of a weird thing to explain. So basically, if you have some kind of picture, let me draw it down here. Let's say I have some kind of function that looks like this, and I want to talk about where something is concave up and concave down. It would be what I call concave down from there to there, and then concave up from between those 2 points, and concave down from there to around there, and then concave up after. Can you guys kind of see what concavity is? Like where it's like bending upwards or bending downwards? Some textbooks have, described it before as holding water, but I don't really like that definition for concavity, for concave up, because, 1 over x is what we call concave up, but it doesn't hold water. The water would flow right after that, right? So does that make sense? So concave up is going to be where it kind of bends upwards. Concave down is where it kind of bends downwards. All right, the formal definition is if you have something that's concave down, all of the tangent lines, when you draw them in, they'll be above the curve. So if you look at our first picture, this is what we call concave down. So it's kind of bending downwards. And all of the tangent lines are drawn above it. Now, if you look at the slopes, our slope started out pretty steep at 4/3, then it went to 1, then 2/3, then 2/7. And then on this side, it's actually negative, right? So our slopes are decreasing, right? They're getting smaller. Okay, so when you say the slope is decreasing, what that means is if I take the second derivative, the slope of the slope, it's negative. Does that make sense? Okay, so if I talk about concave up is going to be where all of the tangent lines are below the curve, right? And all of those tangent lines are actually, as you move from the left to the right, they're getting steeper, right? So the slope of the tangent lines are increasing, so the second derivative is positive. Does that make sense when you talk about concavity? All right, so the definition that I use for concave up and concave down, it has to do with the second derivative. So if the second derivative is positive, right, then it's going to be concave up. And if your second derivative is negative, then your graph is concave down. Okay, an inflection point, if you look at my picture from before, the inflection points are the points where your concavity is changing from down to up or up to down or whatever. Does that make sense? There's a point kind of in between the curve where it's doing that transition. Okay, those are called inflection points. All right, so number 1, so it says determine where the graph of f of x equals x to the 4th minus 6x squared plus 1 is concave up and concave down. Find any inflection points and draw a graph. Okay, so we're going to go ahead and find the first derivative. So I get 4x cubed minus 12x. And then I find the second derivative, which is 12x squared minus 12. So I want to set the second derivative equal to 0. It's very similar to finding critical points, but we don't call these critical points. We call them points of interest. Think of inflection point, point of interest. All right, so I get x equals -1 and I get x equals 1. So these are possibilities for points of inflection. They don't have to be points of inflection. They could be. All right, so we put those on a number line, just like we did with the first derivative, and we test in each location. So if I test -2, I get 12 times a negative number times a negative number is a positive number. If I try 0, I get positive, positive, and negative make negative. If I try 2, I get positive, 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 make positive. Okay, so instead of, do you guys remember with increasing and decreasing, we did up, down, up? We don't do that here, okay, because we're not talking about whether the function is going up or down, right? What we're talking about is where f is concave up or concave down. Okay, so what we do is concave up, concave down, concave up. Now think about the original function. Looking at f of x equals x to the 4th minus 6x squared plus 1. Okay, what do we think that shape is? What does it look like when you graph it? X to the 4th minus x squared. Okay, it's like a W shape. Does this make sense based on our up, down, up thing? Yeah, it does. Up, down, up, right? So far we're good. So always kind of check yourself based on the original. All right, so if I'm graphing this, right, I have inflection points at -1 and 1. I need to find what those actual points are. So I'm going to find f of -1 and f of 1. So if I plug in 1, I get 1 minus 6 plus 1, so I get -4. I actually get exactly the same thing for -1. Okay, do you remember the even functions, even versus odd? This is an even function because if I plug in a positive x or a negative x, I actually get the same value because all of the powers are even. right? So I'm going to have 1 and negative 4, and negative 1 and negative 4. Okay, but that's not really helping me as I'm graphing this, because that's just my inflection points, right? That doesn't really help us when we graph it. So we actually should probably find our maximums and minimums as well. So that's what you guys did for your homework. So if I, whoops, not that one. If I set my first derivative equal to 0, right, I'm going to pull out the 4x, and I'm going to have x squared minus 3. So I'm going to get x equals 0 and x equals plus or minus root 3. And if you put those on a number line, we can kind of cheat a little bit because we know what this shape looks like. We just kind of confirmed it too with our second derivative. It's like a W shape, right? So it should go down, up, right? So you can check. You would get negative, negative, and positive if you check. So we should have minimums at the root 3 and negative root 3, and we should have a max at 0. So we go ahead and we plug those in. So we find f of 0, f of root 3, and f of negative root 3. So f of 0 is easy. It's 0. Actually not. It's 1. I was looking at my first derivative. It's 1. All right, and if I plug in f of root 3, do you guys know root 3 to the 4th? Our shadow guest got that earlier today. Root 3 raised to the 4th. It is 9, yes, because it's the same as like 3 squared, right? Square, square. So we get 9. So we have 9 minus 6 times root 3 squared is going to be 3 plus 1. So we have 9 minus 18 is negative 9 plus 1 is negative 8. We actually get the same for both of those, again, because it's an even function. So root 3 is somewhere around 1.7. So when we graph it, we're going to go almost to negative 2, and we're going to go down to negative 8. Okay, and those are going to be the minimums. So I'm going to draw like a little bump there, so I know that those are going to be minimums. And then 0, 1 was the maximum. So we'll draw a little bump there too. And then we just connect those points. Now the inflection point should always kind of work out in the end. Like when you connect your maximums and minimums and so on, it should kind of look like where it should be, right? So it does look like that's where it's kind of changing from concave up to concave down. So you guys see how this is concave down until we get there, and then all of a sudden it's concave up. Does that make sense? You guys see it? Okay. So that's our graph. Good? All right, so if I was answering all these questions, it's concave up on the interval negative infinity to negative 1, and then again from 1 to infinity. It's concave down from negative 1 to 1, and there's inflection points of negative 1, 4, and positive 1, sorry, negative 1, negative 4, and positive 1, negative 4 as well. Okay, so I answered all the questions. That's not an interval for the points, right? All right, so number 2, so sketch a graph of the curve, labeling all points of inflection and extremes. It's the same thing, but now I know that I have to find all the extreme, I have to find all the maximums. So we're just gonna, as we go through, we're gonna find where our original, our f prime equals 0, right? Where f double prime equals 0, and so on. Find all the y values for those. Okay, so go ahead and kind of do it along with me. So find the first derivative, find the second derivative, set them equal to 0. So when you find y prime, you should get 4x cubed minus 12x squared, which factors by pulling out a 4x squared. So you have 4x squared times x minus 3. So you get critical values of 0 and 3. All right, so if I'm testing in the first derivative, I try a negative number. This first part, the 4x squared, is always positive. So don't worry about that, that's positive. So negative 1 minus 1 is negative. And then if I try 1, I get a negative. And if I try 3 or 4, I get a positive, right? Usually when something has multiplicity in the derivatives, you see how 0 was a 0 twice? That's when it's not going to alternate. So it did not alternate here. It became negative, negative, right? All right, so that means our function is going to go down, down, and then up. So f of x does that. So if I was doing a little rough sketch off to the side, I'd be like, okay, it's going to go down. It's going to taper off to a slope of 0. and then it's going to go down again, and then it's going to go back up, okay? And if you think about it, if you guys are really good at knowing what your functions, like what polynomials look like, we have x to the fourth, meaning our end behavior is both up, like both of them, the ends are pointing up. But the negative x cubed is right here. Do you guys see how that's kind of like negative x cubed? Okay, same idea for the w. Like x to the fourth, that's when they both go up. But when you subtract out an x squared, that's what makes the w shape, because that's a negative x squared in there. Okay, so this can kind of help you if you know those things about graphs. It helps you as you're graphing them. All right, so I want to find y double prime. So I'm going to have 12x squared minus 24x. I pull out a 12x, and when I do, I get x minus 2. So I have x equals 0, and I have x equals 2. So those are my second derivatives, so I put in 0 and 2. And then I test in the second derivative. If I try negative 1, I get negative times negative is a positive. If I try 1, I get positive times a negative is a negative. If I try 3, I get positive times positive is a positive. So it means my graph is up, down, up. Does it look that way for my little rough sketch? Yep, it was concave up there, and then it was concave down, and then it was concave up, right? So we're good. All right, so we're going to need to know a couple values. We need to know where this 0 is happening. It's not a max or a min or anything, but it's an important point. It's where it's kind of making that little x cubed shape. So if I plug in 0 into the original, I get 0, 0. If I plug in 3 into the original, I get 3, comma, 81 minus 4 times 27. Is it negative 27? Yeah, negative 27. See, I'm tricky. I did a factoring trick. This is how you can do mental math, guys. So 81 I knew was 27 times 3. So I pulled out the 27, and then I thought about 3 minus 4. Does that make sense? Tricky, tricky mental math. You're like, no, never. All right, and then this one, again, is 0, 0, and if I plug in 2, I have 16 minus 32, so negative 16. Okay, so those are my important points. So the 3, comma, negative 7 is going to be a min, and then these are going to be points of inflection because it changed from concave up to concave down or down to up. Okay? So putting it all together, I have 0, 0, that's where it's going to go. From decreasing, taper off to a slope of 0, and then decrease some more. And then we're going to have 2, comma, negative 16 is going to be a point of inflection. And then we're going to have 3, comma, negative 27 is going to be a minimum. So draw that little bump there. So it goes up like that. Now this one would not be hard to find the y-intercept or the x-intercept as well. If you set your original equal to 0 and you pulled out the common factor, so you guys see how you have an x cubed in common and then you have x minus 4? So the y-intercept should be 0 and 4. Okay, but it's really difficult as a math teacher to make something where the original function factors, the first derivative and second derivative factor. Okay, this is a very rare function where it worked out nice. So it would actually cross right here if you wanted to be very specific. But a lot of times those are not nice numbers. All right. Okay. All right, so moving on to something called the second derivative test. So it would be nice if the AP test always gave you functions. And before, like 1998, like when Mr. Crawley took the AP test, you guys know we had the same math teacher by that, Mr. Crawley. We had the same calculus teacher. Weird. But when he took the AP test, it was very like function-based. Okay, the whole test was they gave you a function, you had to take the derivative. It was very like normal Calc 1 in college. Okay, the AP test is very tricky. The AP test now has tables, it has graphs, it has functions. So sometimes you don't know what the function is. Maybe there's just a graph or there's a table. We don't know what f of x is originally. Okay, so when we have something like a chart, that's when the second derivative test works the best. Okay, so the second derivative test, kind of think through what it's saying. So it says if f prime of c is equal to 0, that means their slope is 0. So what could happen when the slope is equal to 0? One of 3 things. Max, min, or what? The little x cubed shape. Yeah, or I guess, are you saying just straight across? I guess that's 4 things, right? So you could have something like that. But then it also says the second derivative is greater than 0. So that means that it's concave up, right? So if you have something where you have concave up and the slope is equal to 0 at that point. What do you have to have? A minimum, right? So then f has a, we'll say, local minimum. We don't know if it's the absolute, but definitely a local minimum there. All right, and then the second part says, well, if f double prime is less than 0, so if I'm concave down and my slope is equal to 0, right, then that's when f has a local maximum. And then there's actually a third part of this that says, if f prime of c is equal to 0 and f double prime is also equal to 0, then we can't tell what's happening. Okay, then you would need more information. So that's kind of the third part of the derivative test. Okay, so number 1. So it says find the relative extrema using the second derivative test. Okay, so we're going to find f prime of x first. So I'm going to get negative 15x to the fourth plus 15x squared. And I set it equal to 0 to find my critical values. So I'm going to pull out a negative 15x squared. So I have x squared minus 1. So it factors into x plus 1, x minus 1, and that negative 15x squared. So I get 3 critical values. I get 0, negative 1, and 1. Okay. Those are locations of possible maxes and mins. We don't know. Okay. So what we can do, instead of finding where it's plus, minus, plus, I mean, yeah, you could do that for this one because you have the function. If you didn't have a function and you instead had some kind of chart, that's when you'd have to definitely use the second derivative test, and that's the next problem. Okay, so let's go ahead and, we're not going to do our little number line. We're now going to find f double prime. So when I do this, I get negative 60x cubed plus 30x. All right, I took the second derivative. So from here, going down there. And I set it equal to, well, no, I don't actually need to set it equal to 0. What am I doing? So now I find f double prime of 0, f double prime of negative 1, and f double prime of 1, because I want to know if it's concave up or concave down at each of those locations. Okay. So if I have f double prime of 0, right, I get 0. That doesn't tell us anything. But if I do f double prime of negative 1, I get negative 3 times negative 1, so, no wait, negative 60 times negative 1, so 60, minus 30, so I get 30. That's telling me that my second derivative is greater than 0, it's positive. So I'm concave up. But at negative 1, my slope was 0, right? It has to be that bottom point. So there's a minimum at x equals negative 1 by the second derivative test. Does that make sense? And then if I plug in 1, I get negative 60 plus 30. That's a negative number. So that tells me that I'm concave down at 1. But the slope at 1 is also 0. So there's a max at x equals 1. So if you didn't have the function and you knew that the first derivative was equal to 0 at 0 and the second derivative was equal to 0 at 0, we don't know anything about that graph. We don't know what's happening. There could be a max, there could be a min, there could be none of the above, right? It could be like x cubed, right? It could be something like that. So we don't know what's happening. Okay, so that's when we need a little bit more information. So let's go ahead and do our number line. Just for the 0, we want to know what's happening at 0. So if I plug in like negative 0.5 into the first derivative into here, this part out front is always negative. Negative 15 times the positive number. Okay, so it's negative. Negative 0.5 gives me positive for the next one, negative for the next one. So negative times negative is a positive. So what happens when you plug in 0.5? Negative out front, positive, negative, positive. So do you guys see that we have to have, like it's increasing and then increasing again? It's one of those things where we're doing this. Okay? So this is neither. It's not a max or a min. So in the other class I said, well, that always happens. Like if f double prime equals 0 and f prime equals 0, is it always like one of the x cubed functions? It's not. Okay, so the one that I want you guys to think in the back of your head about is y equals x to the fourth. Okay, take the first derivative, take the second derivative. First derivative is 4x cubed. Second derivative is 12x squared. So x equals 0 is, we call them, like I said, points of interest, right? It's a thing that could be an inflection point. Okay? So if I plug that into the second derivative, if I try like a negative number and a positive number, both of them give me positive. Okay, that's one that's a minimum. Okay, so the last one was one of the things like x cubed where it tapered off and then went back up. But this one, if you graph x to the fourth, it looks like this. It's just like x squared, except it's a little bit more flat between -1 and 1. What did I do? Huh? No, because when you plug in a negative number into the second derivative, yeah, you get a positive regardless. Okay, so it's not a point of inflection then. So think about all of the weird cases. These are good things to like put on note cards, thinking about weird cases for things, right? For first derivatives, we had like the cube root of x, we had the absolute value of x, right? There's things that can be weird for first derivatives, right? Second derivatives, x to the fourth is a good one to always think about. Okay, because just because the second derivative equals 0 at 0, it does not mean that you have a point of inflection. It went from positive to positive, right? All right, so this one's a little bit weird. All right, I had something strange here, so I'm going to go ahead and put, instead of undefined, let's put 0. Because I was trying to think of a function where the first derivative is undefined, but the second derivative is 0, and I couldn't think of one. So maybe there is one, but I got to think about it a little bit. All right, so number 2a. So it says identify all x values where f has a relative minimum justified. Okay, so if we're going to have a relative minimum, we need to find places where f prime equals 0 or f prime is undefined, right? Because we could have something like an absolute value function or something where we have a minimum still. Okay, so looking at our chart, here's f prime in this row. F prime is equal to 0 here, here, and I had you guys edit this one as 0 as well. So these are 3 locations of possible minimums or maximums. Okay. Using the second derivative, the second derivative at x equals -1 is -1. So this means that we're concave down, but our slope is equal to 0, right? So what do we have there? We have a maximum, right? So what about the next one? This is where we have concave up, but our slope is equal to 0. Is that a minimum? Yeah, that has to be a minimum. And then the next one is 0 and 0. It could be something like that x to the fourth that we just talked about, right? Where the first derivative and second derivative are equal to 0. So let's use the values that are next to it. If I had put this on a number line, if I put 7 on the number line, and I tested on the left and the right of 7, look at the 2 values that are on the left and the right for the derivative. The first derivative is positive and then positive. Does that work? Does that become, so that give you a slope of 0 or anything? No, so that's not going to be a minimum either. All right, so for this we're going to say that there's a relative minimum at x equals 0, or no, x equals 3, because f prime of 3 is equal to 0, and f double prime of 3 is greater than 0, or you could say equals 2, right? So this is by the second derivative test. Now someone in the first class asked, can I just say by the second derivative test? I would list these somewhere, because a lot of times you get a point just for like listing those things, right? All right, so for the same reason, where does it have a relative max? Well, that's going to be right here, right? So we're going to have, there is a relative max or local max at x equals -1, because f prime of -1 equals 0, and f double prime of -1 is negative, right? So again, by the second derivative test. So identify all x values where f has a point of inflection and justify. And this is where I think I need to really think about this last part of the table, because if that one was increasing and then increasing again, there should actually be a point of inflection there. But based on my table, I don't have it happening, right? It doesn't change from positive to negative or negative to positive for my second derivative. So I think I've made an error in my table. I need to think about it a little bit. But anyway, we'll skip that one. So if I have a point of inflection, so my points of inflection can occur at 3 different, or there's a possibilities at 2 different places. Okay, so here and here. Sorry, I have that as 0. All right, because that's when my second derivative is 0 or undefined, right? So in order to have a point of inflection, I want my second derivative to change in sign. Okay, that's always an important thing. Whenever you have a point of inflection and it says explain or justify or whatever, your reasoning for a point of inflection should always be the second derivative changes sign. Okay, does it make sense? Like it goes from positive to negative or negative to positive. That's all you need to say. Okay, so in this case, if I look at my second derivatives on the left and the right, does it change signs? Yes. Okay, so there's a point of inflection. At x equals 1, because f double prime changes sign. That's all you need to say. All right, but what about at x equals 7? Does it change sign? 3 to 5, right? No, those are both positive. So it means it was concave up and then concave up again. So this one's a no. So that's the only place. And then the last thing says, what is the equation of the tangent to the curve y equals f of x at x equals 5? So remember, whenever you want an equation of a tangent line, you need the slope, which will be f prime of 5. And we need the point. So it's 5 comma something. So looking at our chart, let's look at 5. So x equals 5's here. Our original point is 5 comma what? 3. Yeah, it's because the f of x is there, right? 5 comma 3. And what's the slope? 2. Do you guys see all that? Can you guys read the chart? All right, so 5 comma 3, and our slope is 2. So if I was writing my equation of my tangent line, it's y minus y1 equals m times x minus x1. Okay, and then the last question has nothing to do with the chart. But I like to ask these on the test. They can be a little bit tricky, but not too bad. So it says, sketch the graph of a function f having the given characteristics. So it says f of 2 and f of 4 are both equal to 0. So those are telling us points on our graph. We have to have 2 comma 0 and we have to have 4 comma 0. So we have to have those 2 points in our graph. And then it gets a little confusing because it says f prime of x is greater than 0 for x values less than 3. F prime of 3 does not exist. F prime of x is less than 0 for x is greater than 3. And f double prime is greater than 0 for x is not equal to 3. Okay, that's a lot of information to process. So sometimes when I do these types of problems, I like to write my little number line off to the side. So I'm going to do it for f prime and f double prime. So we said that f prime of 3 does not exist. It's undefined, right? The slope is undefined. But when I'm on the left, when x values are less than 3, my slope is positive. And when I'm on the right, my slope is negative. So that means I want a function that increases and then decreases. Is there a maximum in between them? Maybe, but not necessarily, right? What else could I have in between them if the slope is undefined? Now, what do you think, Spencer? An asymptote, right? So you could have an asymptote, you could have a corner or a cusp. Okay, that's the only things that you can have there. All right, and then it says that f prime is positive except at 3, which we don't know what it is at 3. So we don't know like the second derivative at 3, but we know that it's positive everywhere else. So what we're saying then is it's always concave up. Okay, so think about what a graph could look like. So Spencer said we could have an asymptote. So let's say we have an asymptote. We're going to be increasing and concave up for the first part, going through that point. And then we're going to be decreasing and concave up for the second part. Does that make sense? So that's one thing that could work. But there's lots of possibilities. So another thing that could work is you could have your points through 2 and 4, but then maybe we do have a maximum. Just because the slope is undefined there doesn't mean that there's not a maximum. There could be a corner or a cusp. Okay, but we definitely need our concavity to work. It can't just be an absolute value function. Do you guys understand this? So we can't just have like this, because we have no concavity, right? It's not concave up or concave down there. The second derivative is equal to 0. Okay, so we would need it to go like up like this, hit some kind of point, and then go down like that. So see how they're both concave up, but increasing and then decreasing. Does that make sense? So I like to put those types of questions on the test. All right. It's hard for me to grade, but that's check to see if you know all the stuff that you're talking about. Did I stop it?
He's right.